Hello, everyone. So we are going to continue on with gases. So we were looking at the different gas laws. No, we don't want that. And we had played around with using these different equations. So like P1 V1 equals P2 V2, so on and so on. And then we talked about the ideal gas law. So if we're frozen in time, we can relate pressure, volume to amount and temperature through this constant. And, our gas constant R is 0.0821 liters times ATM over moles Kelvin. So when we use PivNert, make sure you're honoring the units of your R value. Now, one nifty thing is this STP, or the standard temperature and pressure. So if I am set at 1 ATM and 1 ATM and 0 degrees Celsius, I could plug that information into PivNert to go from, say, amount to volume, or volume to amount. But because these things are standards, we can actually set up this ratio for gases, which lets us know that 1 mole of any gas, this doesn't include solids or liquids, but 1 mole of any gas is equivalent to 22.4 liters. So now we can hop back and forth between moles and liters pretty quickly. And let's do that. So I've got a problem here that says, hey, what volume will be occupied by 28.4 grams of propane? And it says it's at standard temperature and pressure. So if you're at standard temperature and pressure, you want to use one of the nifty tricks. Now, I can relate moles to liters. This problem, though, gave me information not in moles, but it gave it to me in grams. That's okay. Hopefully by now you're starting to see that grams and liters, or rather grams and moles, are one and the same, just changing them out through molar mass. So I've got 28.4 grams, and it gives me what the material is. It says it's propane. So 1 mole of propane, C3H8, will weigh, let's see, 12, 36 plus another 8 is going to be 44, I believe. Yeah, 44.1. 44.1 grams, C3H8. So grams will cancel, and now we have moles of the propane. Now, if I want to go from moles into liters, we get to use this nifty thing because it tells us we're at STP. So I'm going to just use this relationship here. I want to get out of moles, so I'm going to put the 1 mole on the bottom. And it says that that will yield 22.4 liters of the C3H8. The mole will cancel and we'll be left with just liters. And in this case, we have 14.4 liters. Now, let's say you forgot that nifty trick of STP in this equation here. You could have just plugged all the information into PivNert with the temperature being at 273 Kelvin and the pressure being 1 ATM. It would give you the same answer. So it's up to you. I want you to do this one here, all right? So this is saying how many grams of nitrogen will be in 1.50 liter of 1.50 liter flask at STP. One thing I want to tell you though is nitrogen as a gas is going to be N2. Okay, so just take that into account. So you know something about the volume. I want to know something about the amount. I'll give you all 3 minutes for that one. It's really just the reverse of what we did on the previous guy. All right, so this one is giving us information about the volume. It says we're at STP. So if you're at standard temperature and pressure, just give yourselves a heads up that you've got a special set of conditions that actually makes the problem a little easier. So I'm going to start with my given, which is the liters. So I have 1.50 liters of, and this is specifically N2 gas. All right, well, if I'm at STP, for every 1 mole of nitrogen gas, it will be equivalent to 22.4 liters of an N2 gas. All right, that gets me out of liters and it gets me into the amount of the gas. The problem just says, hey, refine it from moles into specifically grams. So for every 1 mole of nitrogen gas, I weigh 28 grams, because we're dealing with a diatomic. So each one of those molecules is actually going to be 2 nitrogens strapped together. So make sure you're taking that into account. Those will cancel, and we're left with 1.88 grams of N2. So kind of a nifty trick when we're at STP. Again, if you forgot that relationship on an exam, you could always go back to using PivNert. Let's move on to gas stoichiometry. All right, so in our PivNert equation up here, there is an N amount. and N is in moles. Anytime we can get a value of moles of something, we can play around with stoichiometry as long as we have a balanced equation. So remember, stoichiometry is looking at the coefficients in a balanced equation will give us the molar ratio. So for instance, down here, if we take C2H4 and we combust it with oxygen to give us CO2 and H2O, we have these coefficients that sit in the front. Those give us a mole relationship. 1 mole of this needs to combine with 3 moles of this, and they will yield 2 moles of this and 2 moles of the water. Now, a nifty tool when we're dealing with gases, and this is again only for gases, when you're at a constant temperature and pressure, and it doesn't have to be standard temperature and pressure, so it doesn't have to be 0 degrees Celsius and 1 atm. It just needs to be constant. There's no change to your temperature and pressure. The coefficients will actually become a liter to liter ratio as well. So not only are they a mole to mole ratio, but they're a liter to liter ratio. And if you want to look at this example here, so this is like saying, hey, 1 liter of this gas will combine with 3 liters of this gas, and it produces 2 liters of this gas and 2 liters of this gas. Okay, so take note of that. Let's try a simple one here. So it says, using this equation, 1.30 liters of ethene, the C2H4, are burned completely. What volume of the O2 is required if both gas volumes are measured at constant temperature and pressure? So it's telling you in the problem, hey, you get to use that liter to liter direct ratio because we're not changing temperature and pressure. So let's set it up. And what we'll find is that, where was our given? 1.3 liters of the ethene. And we know that for every 1 liter of ethene, 1 liter of C2H4, we will need 3 liters of the O2 to balance it out. Okay, so the relationship is, 3 of these for every 1 of these. So this here cancels, and we can real simply just take our initial value and multiply it by 3, where we find that we have 3.90 liters of O2. I want you to try this one here, D. D is kind of like a limiting reactant problem, but we're using liter amounts, okay? So you're given, instead of given mass amount or mole amount, you're given liter amount. So you have 240 liters of NO gas, and you have 155 liters of O2 gas. I want to know, in theory, how much NO2 could you produce if you're at constant temperature and pressure? If you're at constant T and P, you get to use the direct liter to liter relationship. So I'll give you all 4 minutes to set that up. It's kind of like doing the first part here, but doing it twice. All right, so just like the first one, I see this thing telling me, hey, it's constant temperature and pressure, and it's giving me information in liters. This whole equation is all gases, so I know I can jump liter to liter. So if I've got 240.0 liters of the NO, and I want to jump into or figure out what volume of NO2 I have, I just use my coefficient, which tells me that for every 2 liters of the NO, I will get 2 liters of the NO2. So it's a 2 to 2 or 1 to 1 ratio. So for that guy, it'll just be 240. 240.0 liters of NO2. Then I want to run through the same thing with the second here. So if I have 155 liters of O2, I'm going to jump from my O2 into my NO2. And in this one, we've got one O2 liter will yield 2 liters of the NO2. All right, so in this case, we need to multiply by 2. So we get 310 liters of the NO2. So it's a limiting reactant problem. So we're only as good as our least amount, right? I don't have enough of this NO to produce that full 310. So my theoretical yield or my theoretical volume here is going to be the 240, and my limiting reactant is the NO. This would be our limiting reactant. So next problem is relating materials where we have solids. So these equations up here where we were able to go directly from liter to liter, this is all looking at everything in there as gases. Here I've got a solid of one thing, I've got gases of other things and liquids. And so we're going to have to do a combination of stoichiometry along with PivNert, or PV equals nRT. So here we say that lithium hydroxide is used in a spacecraft to recondition the air by absorbing the carbon dioxide. So the lithium hydroxide absorbs the carbon dioxide and it will produce this lithium carbonate and water. So what volume of carbon dioxide gas, so we're trying to find the volume of carbon dioxide gas at 21 degrees Celsius and 781 mmHgs could be absorbed by 327 grams of lithium hydroxide. So there's two different sets of information here. One is talking about carbon dioxide. The other one is talking about lithium hydroxide. So if I want to find volume, I can use PivNert for CO2. So PivNert, PV equals nRT. If I want to solve just for my volume, I can move my pressure over to the other side. And we'll get rid of this here. So in order to get volume, I need to know a bunch of things about the carbon dioxide. I need to know the amount of carbon dioxide. That I don't currently know. R is a constant, T is my temperature, P is my pressure. So I have everything in this equation minus the amount of CO2. That isn't given, but you know what is given is the amount of lithium hydroxide. And if I know the amount of one thing in a balanced equation, I can really easily find the amount of something else by going through that process of stoichiometry. So 327 grams of LiOH. In order to go from 2 to 1, I need to get this out of grams and into moles because I can't do any sort of stoichiometry in a mass value. So for every 1 mole of lithium hydroxide, this thing weighs 23.95 grams. 23. Oh, hard for me to write on this. 0.95 grams of LiOH. Now I can jump from the amount of lithium in moles to the amount of CO2 in moles because coefficients give us that ratio. So 2 moles of this LiOH are going to yield 1 mole of CO2. Now, in this equation of PivNert, my amount is in moles. So I don't need to go back into grams. I don't need grams of CO2. I can actually just stop here and figure out my moles of CO2. So when plugging this in to moles of CO2, I end up with 6.83 moles of CO2. Now, volume is going to equal my moles. So I get my 6.83 moles times my R, which is that 0.0821, and it's liter ATM mole Kelvin, right? Times my temperature. They give me temperature in Celsius. Temperature in these equations needs to be in Kelvin. So add your 273 to the 21, which will give you 293 Kelvin. And then over our pressure here, 781 mmHgs. We don't want mmHgs. What do we want for pressure? We need ATM. So we're going to take this number and we divide by the 760 mmHgs for every 1 ATM. And our ATM here becomes 1.03 ATM. So we've combined our stoichiometry to get the amount to then use PivNert. Moles will cancel, Kelvins will cancel, ATMs will cancel, and we'll be left with, let me clear that up, that is supposed to be an L, liters. So this whole number here, 1.60 liters of CO2. Any questions on that one as far as how we got that? So you will be expected to combine gas laws and stoichiometry. All right, let's try some other word problems. So an automobile airbag is inflated by nitrogen gas at a rapid decomposition of this sodium azide. So we've got sodium azide, it's in the airbag, and it will decompose into sodium and then the N2 gas. The N2 gas is what's that rapid filling up of your airbag. So if an airbag has a volume of 36 liters and is to be filled with nitrogen gas at 1.15 ATM and 26 degrees Celsius, how many grams of NaNO3 must be decomposed? So I want you to try this one here. This is a problem similar to here where we have to combine PivNert and stoichiometry, but we're going in the opposite direction. You're given a bunch of information about your nitrogen. You need to figure out how much nitrogen there is so that you can then figure out how much of the solid there are. So I'll give you all 5 minutes for that.
Can you scroll down just the slightest bit so I can see the problem right above it and kind of cross-reference?
Yeah, totally. Just note though, here you were finding, you did your stoichiometry first and then plugged it into PivNert. This problem, you're gonna wanna plug information into PivNert first and then work backwards, okay? So you start with figuring out the amount of this, then go to the amount of this. Okay, so in this equation, we're given a bunch of information about our gas, specifically the volume, the pressure, the temperature. So I can really easily find the amount of gas that's associated with those constraints. My pressure is in ATMs, so I can already just plug that in, right, of 1.15 ATM. My volume is in liters, so I've got 36 liters, 36 liters. My R is a constant, so we've got our 0.0821. I'm not going to put all the units in there. And then our temperature is 26. So that is the one thing that we do have to adjust, taking our 26 and adding to 273. And that gives us a temperature of 299 Kelvin. So we're taking our ATM 1.15. We're going to multiply it by our volume, which in this case is 36. Let's divide it by that constant, 0.0821. And then we're going to divide that number by the 299. And what we get is that we know our N value, or our amount value for this N2 gas, is 1.69 moles of N2. Okay, the value of N is popping out in mole. So now I can do stoichiometry, because the problem is not asking me how much of the N2 gas there is, but how much of this do I need to have in the airbag. So my relationship here, for every 3 moles of N2, you will produce 2 moles, 2 moles of the NaN3. So 2 moles, the NaN3. And then to refine it, it says, hey, let me just know that it's what it is in grams. So we'll find the molar mass of this thing. So for every 1 mole of NaN3, it weighs 14 times 3 plus the 22.99, 64.99. 64. Oh, this pen is not working for me today. Okay, there's a point there. Grams. Grams of the NaN3. So when I plug that into my calculator, taking the 1.69 times the 2 divided by the 3 and times the 64, I get a total mass value of 73.3 grams. So 73.3 grams of this NaN3. There are 2 more problems that you can practice on your own if you'd like. They're in the guided notes, so and the answers are in there as well on Moodle, so if you want to do a little bit more practice. But we're going to keep moving on. The next section here is talking about densities of gases. So remember what density equals. Density is equal to mass over volume. Now, when using density to describe gases, we usually are going to be using the units of density is going to be in grams per liter. Okay, kind of more used to density being in grams per milliliter, but because gases have such a low density, because they have very, very little mass in whatever volume they're in, we're going to stretch out that volume to a liter. Now, by taking density, because it's mass and volume, these are both volume is something we find in our PivNert, and mass is something that we find in molar mass, which then can be converted into moles, which we also find in PivNert. We can actually derive an equation for density, and density is going to equal your pressure times your molar mass. Okay, so M in this case is not molarity, it's molar mass. So you need to know the identity of the material or the gas that you're working with in order to figure out the molar mass. All over R, which is a constant, and then T, which is your temperature. And remember, density here is going to be in grams per liter. We can actually rearrange these as well and isolate for our molecular weight, which is the same thing as molar mass. Molecular weight. Molecular weight is going to equal the density of the gas times this R value times temperature all over pressure. Neither of these work for solids or liquids, okay? Everything here is only going to work for our gases. So let's try this one here. We've got a set of parameters. It says what volume will be occupied by 0.393 moles of N2 at 738 torr and 24 degrees Celsius. And then it also says what is the density of N2. So the first part for volume, we can use our PivNert equation, PV equals nRT. And if I isolate for V, volume will equal nRT all over P. I know each of these things. I know the amount in moles, it's right there. So 0.393 times my R, which is the 0.0821 with the funky units. Temperature, 24 degrees Celsius. So we need to convert that, 24 degrees C. Take your 24 and add 273 and we get 297 Kelvin, 297 Kelvin. Put this whole thing over our pressure. We're at 738 torr. We don't want to be in torr. We want to be in ATM. Remember, torr is equivalent to an mmHg, and for every 1 ATM, there are 760. So we take this number and divide it by 760, or this thing here tells me I've got 0.971 ATMs. So finding my volume here, I'm just going to take the 0.393 times our constant times my temperature, 297, and divide that whole thing by my pressure, 0.971. And this gives me a volume of 9.87, and the units are going to be liters on that. That's nothing new. We've already worked with that. Okay, so that's sort of just a review of PivNert. But the second thing is saying, hey, can you tell me the density of this? And we can. So one thing we could do is take my moles and convert it into grams and then divide it by however many liters we have. Or let's try and use the equation just in case that first part of the problem wasn't there for you. So we have density is going to equal my pressure times my molar mass all over my R times my temperature. So my pressure is the 738, but again, we want that to be in ATMs. So 738, I forgot what it was, 730. 738. Or we got 0.971. So 0.971 ATM. We multiply that by the molar mass. So the molar mass of N2 is going to be 28 grams per mole because diatomic. Okay, so double it up if it's a N2. We're going to see a lot of diatomics with our gases. Our R constant 0.0821 liters, ATM, mole, Kelvin. And then we're going to multiply it by our temperature, 224 plus the 273, 297. And let's see what happens with the units. Kelvins cancel, ATMs cancel, moles cancel. Sorry, there's my Kelvin. And we'll be left with grams per liter, which is in fact the unit that we want to use for density. So just plug that in, 0.971 times 28. I'm running that through your calculator. You get a 1.11 and the units gram per liter. So that would be our density. So I want you to try this one here, number 2. So this is an unknown liquid. And what you're trying to do is calculate the molar mass. Okay, I want you to tell me what the molar mass is. So of these, if we're going to calculate molar mass, I want this bad boy over here. So using this equation here, see if you can come up with the molar mass using all the other little pieces of info. And I'll give you 5 minutes. So on this one, we have 1.665 grams. We have 125 degrees Celsius. We have a volume of 0.421 liters. And we know the pressure is 749 torr. Make sure you're using the right units too. So in this one, it's asking about molar mass and it's giving us some information about this gas. So we can use our molar mass equation, or rather our molecular weight equation. So molecular weight or molar mass, those are interchangeable, is going to equal your density times your R times your temperature over your pressure. Now remember what density equals. Density is grams over liter. So I'm not given density directly here, but I do have a gram value and I do have a liter value. So I just divide those two by each other. That is my density, 665 grams divided by the 0.421 liters. That whole thing is the density. Then we've got our 0.0821 liter ATM mole Kelvin. Our temperature, which is, well, it's not 125, it's 125 plus the 273, which give us 398 Kelvin. And we put this whole thing over our pressure, which is 749 torr, but we need to get that into ATM. So just divide it by the 760. And we end up with, or was it 0.98, pretty close to 1 ATM, 0.986 ATM. I wrote it all out with the units so we can just make sure that everything is canceling. Liter cancels with liter, Kelvin cancels with Kelvin. And then we have gram and mole. Gram per mole, right? This is under a fraction bar. So that in fact is the unit of molecular weight, or gram per mole. In this case, we end up with 1.31, or no, scratch that. Scratch that. 131.1, and the units are gram per mole. I can't tell you what the unknown liquid is because there are probably quite a few formulas that could come around with this molar mass. So I can only tell you what the molar weight or molar mass is. So next we have this topic or this law known as Dalton's law of partial pressure. What this says is that if I have a mixture of gases, so for instance, the atmosphere is oxygen, nitrogen, there's some argon, there's some CO2. The total pressure will equal, and we can see it here, pressure total equals the pressure of the individual gases added together. So each gas is sort of behaving individually. It's exerting its own pressure, whether the other guys are there or not. So if you just add more of these things, everybody's just kind of doing their job. And to get a net amount or a sum amount, you need to add each individual one together. The equation is quite simple. So if we have something like this, and as far as units are concerned with using Dalton's law, they just all have to be in the same unit. So it's not like this has to be an ATM. This problem here, everything is given in torr, so we can keep it in torr. So it says in a gas mixture, the partial pressure of methane is 150, ethane is 180 torr, and propane is 450 torr. Find the total pressure from that mixture. So I knew the individual amounts. I'm just going to add them together. P total, my total pressure is going to equal each individual component, 150 torr plus the 180 torr plus the 450 torr. We get 780 torr for this mixture. If I had given you the total and given you 2 of the 3 components, you would be able to solve for the third one by subtracting out the other gases. So this Dalton's law of partial pressure comes into play a lot when we're collecting gas. So when you're running an experiment, like let's say we're vaporizing this purple material, if it wasn't in a closed container, what would happen to that vaporized material? It would just go off into the room. We wouldn't collect it. If we want to collect it though, we will usually connect it to a tube that will then pump it into a beaker that's upside down. And this whole system is isolated by water. So the gas can't make its way through the water. So we trap the gas. This is known as collecting gas over water. Now, why that's important is because water itself, depending on what the temperature is there's going to be a certain amount of water vapor sitting in that space above the water. If this is warmer, more water can vaporize. So there's going to be this thing called vapor pressure or water vapor pressure. And that's sort of like background noise. We have to subtract out the water vapor pressure in order to figure out the pressure of just the gas collected. So if we look here, a student, let's say a student is running this experiment here, and they collect, a student collects 355 milliliters of oxygen, and it's saturated with water vapor, and this happens to be at 27 degrees Celsius. Okay, so we've got a student and he says, oh, I've got 355 milliliters of oxygen, but there is some water vapor in there. Now, specifically, and this is going to come off of an appendix, we know that at 27 degrees Celsius, the vapor pressure of water is going to be 26.7 mmHgs. So this is saying what is, sorry, I mixed them up. So this is saying we have 355 liters of oxygen saturated with water vapor. The mixture exerts a total pressure of 775 mmHgs. I was getting these mixed up. So if we have a total pressure of gas of 755 mmHgs, we have to take out whatever the water pressure is. So what is the partial pressure of the oxygen? If I was to write an equation, it would be P total is going to equal the pressure of the oxygen plus the pressure of the H2O. This value, again, is coming off of an appendix somewhere. So that information would be given to you. I wouldn't expect you to know the vapor pressure of water for every temperature. So we know our total value is this. We've got 775 mmHg. I need to subtract out the 260 or 26.7 mmHgs though, in order to get just the oxygen. When we do that, we end up with 748.3 mmHgs. If you were to skip that step and you were to just use this as your total pressure for your oxygen, your pressure would be too high. You would actually be measuring more oxygen gas than is actually there because it's exerting a higher pressure. So if we were to sort of stepstone into another type of problem, how many grams of oxygen does the sample contain? So if we want to find grams of oxygen, well, PivNert is not going to give me grams, but it will give me moles, which is close enough. So I'm going to go with moles are equal to our PV over RT. Pressure is given here. If I used the original pressure without removing the water vapor, my amount is going to come out too big. So we want to use the 748.3 mmHgs. Again, though, anytime we get near PivNert, you want that in ATM. So converting that will be 0.985 ATM. My volume is 355 milliliters. We like that to be in liters. So 0.355 liters. R is our constant, 0.0821 with our funky units. And then our temperature is our 27 plus our 273, which gives us an even 300 Kelvin. So now I can figure out the amount of my gas, which in this case is 0.0142 moles. Does the problem want moles? No, it wants grams. So just a quick conversion, right? 1 mole of O2 is equivalent to 32 grams of O2. 32 because we're dealing with the diatomic. So now I have 0.454 grams of O2. So I was able to figure out how many grams of O2. Again, anytime you see that word vapor pressure, make sure you're taking this step in there. We could even throw a little stoichiometry in there. Why not? For fun. What if it says, hey, tell me something about the solid. So how many grams of the KClO3 would be needed to produce this much oxygen? Well, I've already got my oxygen in moles, so I'm actually just going to use that number there. You could convert this back into moles if you want to, but I'm going to just go from the 0.0142 moles of O2. It's asking about the solid over here. I can just use my ratios, right? So for every 3 moles of O2, we are going to have 2 moles of the KClO3 being decomposed. It says it wants it in grams, so we have to do a quick conversion into grams. So for every 1 mole of KClO3, we will yield 122.5 or 0.6 grams of KClO3. Those moles will cancel, moles of the O2 will cancel, and we can come up with 1.16 grams of the KClO3. So hopefully you all are starting to see how you can interweave our stoichiometry with our gas laws. And note, all these problems here are frozen in time, so we're not using those before and after equations, right? The P1s, B1s, P2, B2s. We use those when we see some sort of change. So the last thing that I want to go over, well, one of the last things is partial pressure and mole fraction. So a mole fraction is the moles of an individual gas divided by the total moles of gas. So if we have a mixture, my equation for my mole fraction is going to be, a lot of times it's denoted as XA, my mole fraction, so the A being the gas that we're looking at specifically, it's going to equal moles of A divided by the total moles. Or sometimes, because N is our abbreviation for moles, we could say N of A, and A being whatever the constituent is, whatever we're trying to look for, NA over N total. Because moles are directly related to pressure, we can also use this equation here that tells us that the partial pressure is equal to the mole fraction, the N1 over the NT, times the total pressure. So if I know my mole fraction, let's say it's 1 to 5, and I know my total pressure, I can figure out the partial pressure. Those are all directly related to each other. So here we've got a problem that sort of ties these two together. It says in the atmosphere, there are 5 moles of air, and that means 1 mole is O2 and 4 moles are N2. So these two things added up give us the total 5. If the total pressure of the sample is 500 torrs, determine the partial pressure of the oxygen and the nitrogen. Well, in order to use this equation, I need to figure out my mole fraction. So my mole fraction for oxygen is 1 out of every 5. So 1 in 5, this is for O2. 1 in 5 is oxygen, and I just multiply that by this, the 500 torr. Or 1/5 of your total pressure, which would give us what, 100 torr? Now, what if we do it for the N2? N2 has a stronger concentration, right? It has a 4 in 5 ratio, 4 moles in every 5 moles of air. I would also multiply that by the total, 500 torr. And what we would get is 400 torr. So remembering that, and this is, sorry, pressure of O2 and pressure of N2. Remember, Dalton's law of partial pressure tells us that the individual pressures, if we add those together, they should equal the total pressure. That's why we get to do that nifty trick with the mole fraction. So everything we've talked about thus far has been in reference to what are called ideal gases. And the kinetic molecular theory is a theory that describes the behavior of gases when they're acting ideally. Now, they don't always act ideal. Most times they're not ideal gases, but these equations work well enough that we can use them, 98% of the time. Here's some of the things that go along with the kinetic molecular theory. The first one says gases consist of a large number of molecules that are continuous and in random motion. So in order for you to be able to use these equations, you have to be okay with that assumption that gases are a lot of molecules and they are moving randomly. The next thing that you have to assume is this thing here, B, which says the combined volume of all the molecules of gas is negligible relative to the total volume in which the gas is contained. This is where the theory starts to fall apart. So what it's saying is that the volume of your gases is so small that it doesn't have an effect on the total volume. So if I have a liter of gas, or if I have a liter container and I have, N2 gas in it, that the N2 doesn't eat away at any of that liter. That's not necessarily true. When we get higher concentrations of gas, they do actually start to occupy some space. So that can start to fall apart. But using the kinetic theory and allowing us to use these rules, we sort of make that assumption. C tells us attractive and repulsive forces between gas molecules are negligible. So the gas molecules have so much energy to them that when they fly past each other, they don't stick to each other at all, or they don't repel each other. They're sort of like billiard balls acting as individual molecules. That also sort of falls apart in certain situations because there can be kind of a sticky quality to gas molecules, especially if it's in a cold and a high pressure environment. And then D, the average kinetic energy of the molecules is proportional to the absolute temperature. So that's just saying you have more kinetic energy when you increase your temperature. This is true. If we pump more heat into a gas, those molecules are going to move a lot faster and they will then go ahead and create more kinetic energy. Now, what is happening in real life are real gases. Real gases, they're not ideal. This means PivNert doesn't always work perfectly. So we may find when we use these equations in certain circumstances that we don't get like the exact number. Maybe it's yielding, hey, you're gonna have 2.5 liters of gas and we end up getting 2.3 liters of gas. Why? Because the gases do interact with each other. They do occupy a little bit of space. Where do these assumptions really start to fall apart? They tend to fall apart at low temperatures when things are colder and at high pressure. So anytime we're forcing the gas into a more close contact environment, they'll start to fall apart. Where are these things ideal? They're ideal, gases are most ideal with high temperature and low pressure. High temperature because they have so much energy that they're moving past each other. They're not interacting with each other at all. So we can kind of think of them as isolated molecules. And then low pressure means they have a lot of space to spread out, again, preventing any sort of interaction between the molecules, and also creates a negligible amount of volume if the density is pretty low. So we tend to like seeing PivNert used when we have high temperature and low pressure environments. Now the last little bit here is there are equations for these two things, for root mean square speed and effusion, and there are these down here, but we're not going to be doing any actual calculations with them. I just want you to understand the concept of this. So the root mean square speed tells me, well, one thing that we already know is that if we increase temperature, we will in turn increase speed. I feel like everybody's good with that, right? The hotter the thing gets, the more the molecules will speed up. But there's another relationship that I want you to know, which is you will have an increase in speed with a smaller molecule or a decrease in molecular mass. So if I have two materials and they're at the same pressure and they're at the same temperature, same volume, everything, one is composed of O2 versus N2. And I would say, which one is moving faster? Which one has molecules moving faster? Well, O2 is bigger than N2. So this guy is smaller and faster. Right? If you go to, throw your 3-year-old, well, don't throw a 3-year-old, let's say 6-year-old, your 6-year-old cousin in the swimming pool. It's much easier to throw your 6-year-old cousin in the swimming pool than it is to throw your 60-year-old father in the swimming pool, right? Smaller, easier to move. As far as effusion just means how quickly a gas will escape through a hole. So how fast gas escapes through a hole. And a confined hole, a small hole, okay? So as far as molar mass is concerned, what do you think? So if we have a large molar mass, a big clunky molecule, do you think it's going to be a quicker effusion or a slower effusion? Well, big clunky molecules are harder to move, so larger molar mass is going to equate to a lower effusion. And vice versa is also true, okay? So a smaller molar mass, tiny things, will escape quickly, or they'll have a large effusion. So if I have two balloons, let's say one balloon is filled with helium, and helium has a molar mass of 4 grams per mole, versus a balloon that's filled with oxygen, which is not as much fun, which is 32 grams per mole. Okay, the helium will float. The oxygen will probably sit on the ground. This is lighter. So if I was to pop a little hole, see this, we got a balloon here and a balloon here. If I was to pop a hole here and pop a hole here, the gas will escape faster in the helium balloon than it will escape in the O2 balloon, as long as the holes are the same. So again, there are specific equations on calculating how quickly this rate of effusion is. You won't be doing the math with it. Just know the concept. All right, and that is gas laws. So we have caught back up, which is great. I want you to make sure you're getting your exam done on Monday or Tuesday. This gas law stuff will not be covered on the test though. All right, this will go on to your 4th test. So, you can mentally drop any of the gas law stuff and work backwards. I'll leave you guys there. Have a good weekend. If you have any questions, feel free to stay around or hit me up with an email. Got any lab questions or anything too, please feel free to stay.